So I'm recording this, and so tell me, what were the experiments that you got done on the lab? Bless you. Let's go ahead and let's draw it again. And you can probably guess that on Friday you're going to get a quiz on the lab portion of last week's the two labs we did last week, because your homework is due on Friday, right? And the homework is designing this lab. So you can guess that this idea that of what is a lab and how do we do this thing we call science, you're going to get some kind of quiz on that on Friday. If you guess that, you're right. Could someone pull that stool down, please? All right. Yeah. Yeah, you should write it down. If you weren't in the lab because you didn't have your safety equipment or you were absent or whatever the situation is, whatever your personal situation is, that's fine. There's if you were, you have to complete the content though. You can't just ignore the content. So your quiz is due whether you're here on Friday, whether you were here or not. This homework is due whether you were on Friday or not, whether you did the lab or not. So that's why you have to pay extra attention the way we're going over the lab right now. Okay, so those people obviously that did the lab have a little bit of an advantage, but we're going over the whole lab right now. Is that correct? Okay. So what is it that you did? Anyone? Yes. All right, so we mixed some chemicals is the first thing we did, right? So the first thing we did, and I'm going to go ahead and write it down this way just so we're all clear. The first thing we did is we had to develop, something's going on with this. Okay, so the first thing we did in the lab is developed our control groups, which then begs the question, what is a control group, right? Does anybody remember from our discussion in class? Okay, so a lot of blank spaces, a lot of tired faces. I know it's Monday, but hopefully we can get a little All right, so our control groups, a control group is a group that you're going to use to compare your data to. So we had in the lab, we had these four. Rather than me defining it any better than that, let me go ahead and draw out the lab, and then when we get to the end, hopefully you understand. So we have these test tubes, right? There were four of them, and they're horribly drawn. I apologize. Not much better, but somewhat. And in one of them we had distilled water, right? DI, distilled water. In another one we had acetic acid, right? ACE. Remember that? Yeah. And we had solid in the other two. It was white, but let me go ahead and change this to white. Maybe I can. We had some.
That's DT.
DI. Huh. So I don't know why it's red. It's so weird. I'm choosing white, but it's. That's good. Come on.
Next to purple. Next to purple.
I did, but it's not. It's still doing a red. It's so weird. I don't know what's going on.
No, your marker is on. Your marker is red. You gotta change it.
I did.
No, you didn't. Go down. You changed the other thing. Go to the thing where it says
stroke. I see. Okay, you're right. Gosh, so bossy.
That's great.
Oh, seriously? Seriously? Is gray not close enough for you?
That's good.
That's good. All right, there.
That's still white.
Okay, white is what we want. So anyways, you had some calcium chloride. Now, I'm going to make a change. I know you used calcium chloride, but the second time you used calcium carbonate. And that's what we should have used is calcium carbonate. Ca. That's right. Ca. Oh, today's not a good day. All right. So we have CaCO3, and that was calcium carbonate. And there's a reason that was important that you use calcium carbonate. So we're going to develop these control groups. And as we did, when we mixed them up, we mixed it up in a different, in a specific combination, didn't we? And we took calcium carbonate or distilled water, and we added it to calcium carbonate, and we took acetic acid, and we added it to calcium carbonate. We got two results, two different sets of results, and what I would like to see before Friday when we look at your homework, what I'd like to see in your write-up, because this is developing your control groups, is some kind of chart, right? So some kind of table that says DI, distilled water, acetic acid, right? And you added calcium carbonate to both. And something happened, so some kind of observations here on what happened during distilled water, and some observations here on what happened during acetic acid. And you were supposed to do this during the lab, weren't you? It said this is part of your instructions. And it said what were the results, and then it asked, the last column should be, was there a chemical reaction or not?
What about the one
Chemical change or not. Remember, a triangle means change. And what was the evidence?
I thought it was inference.
This is the inference, so that's a good question. What is inference? And inference means the observations are here, right? So when you're looking at observations, you're looking at this stuff here, right? This is what you observed.
You said the triangle means
Change, yes, ma'am. So when you're looking at what you observed, what did you see, smell, see? Of course, you didn't smell anything because you're not supposed to in a lab. But you felt warmth, you saw bubbles, whatever happened here. Then you ask yourself, now you're making, based on that, you're inferring whether there is a chemical change or not. There's no guarantee there's a chemical change until you can identify that there's a new substance over here, because that's the definition of a chemical change. You have something new. You're gonna make an inference that a chemical change happened or not based on some evidence, and so that's what I want to see in this column. Yes, question.
When we did the second lab, the colors, you mix the two together and it turned pink, was the other one supposed to change colors too? Because it didn't change colors.
But we'll get there. Can we get there in just a second? Let's finish this one first. So that's kind of what I want to see when you're doing this. All right. This is why I don't like this blue one, this blue background that much. But whatever. All right. So the second experiment, as someone just mentioned, there was a well plate, wasn't there? And you had, I think it was 5, 1, 2, 3, 4, and 5, and then you had a lot of smaller ones here, right?
9.
There were 9. I'm not going to fit 9 on there, but there were 9, yeah. And then you had the objective in one you put in sodium hydroxide, right? Which is a base. Do you remember that? And in the other one, you put in acetic acid. ACE. NaOH. I'm just going to put acetic acid like that. This is an H. All right, NaOH. Now, a lot of people, this is a common mistake, especially since we didn't have time this year to go through all the details of the periodic table. But what you have to understand is when you're describing an element, when you're writing the symbol of an element, you don't put big N, big A. The symbol of an element is big N, little a, lowercase for the second letter always. All right, and no element has more than 2 letters. So Na, then O is, anytime you see a capital letter, it's another element. So sodium, oxygen, hydrogen, sodium hydroxide. And acetic acid's chemical composition is not really important. Just know what's important here is what? That it's an acid, right? Do you agree?
Yes.
Okay. So then, and then the last section, the last thing we did is we put in some what? What was this thing?
pH.
pH indicator. All right. So little p, big H. Notice it's little p first. That lets you know it's not an element. pH indicator. What is an indicator? Something that indicates, something that shows you, a signal, right? As we said, in Britain, they call a turning signal a what? An indicator, right? Just like that's the example we used in class. So a pH indicator is going to tell you if it's something's acid or base. It's going to change color. So people that did the lab, when you put a drop of sodium hydroxide in with a drop of pH indicator, what color did it change?
Pink.
It turned to some kind of pinkish purple, right? All right, so let me see if I can find pinkish purple. What do you say, something like this?
Yeah.
All right,
That's good.
and the film is just that too. All right, so when you mixed, that's the color that it changed into when you mixed in sodium hydroxide and the pH indicator. So we're good with that, right? Turned pink. Now, what did you do what happened when you took the acetic acid and you added the pH indicator to it? So people saw no color change. So it stays clear in the presence of acid.
It was
No, that's correct. That's correct.
So sodium hydroxide, you say, changed color to. All right. So as you add more base to the phenolphthalein, it should turn pink. So you were right. Are we all clear on that? So what did we develop by doing this experiment? Is we developed our known, right? The things that we're going to compare our unknown to, our tests. So there's this hypothesis that we have. And we have to test that hypothesis. And the way we test it is we have to have a known value, a known indicator in this case, that lets us know that something is either calcium carbonate or it isn't calcium carbonate. It's acid or it's base. So that's the two tests that we developed early on in the first day of the experiment. So we have our indicator, we have our different substances. So now let's talk about our unknown. We had an unknown. We had a mistake in the lab, and the person who made the mistake, we had a solid that was white. It was a white solid, right? In a well. And by the way, the other one that we tested that you really should write up as well, but you had calcium chloride, right? And you had some observations on that as well, didn't you? And you said, was there a chemical change or not? Right? And in the calcium chloride, did anything happen in calcium chloride was added to either one, water or acetic acid? Not really, it just kind of became cloudy, right? It kind of turned into a suspension. So no chemical reaction, no change, no chemical change. It did change somewhat because it went into solution, but it didn't really change its chemical composition. Calcium carbonate, though, yes, there was a change. There were bubbles, right? Right? And you all have the data on that. You have the bubbles, some heat. Some people noticed heat in a test tube. There was bubbling. A gas was produced. In other words, what does bubbling mean when there's no... Unless you're boiling something, right? Unless you have heat. When you see bubbles, that means a gas is formed. So you had a solid at room temperature, add something, all of a sudden you start making a gas. It's one of the big signals that you have a chemical reaction. One of those it's from that list that I gave you that I told you better know for the lab. You remember that? What are the signs of a chemical reaction? All right, so you had this solid in a well, and the question was this solid? You don't know what it is. You have no idea what it is. Is this solid, this unknown solid, was it calcium carbonate or was it calcium chloride? You don't know which one it was. And then someone else in the lab also making some really, I guess the person didn't get much sleep the night before. Someone else in the lab also had some liquid in a test tube, but you don't know what it is. You have no idea what the liquid was. So the liquid could be either acetic acid or it could be sodium hydroxide. So your job by Friday is to design an experiment. The first thing you do is create a hypothesis, right? So let's go down the list of things you're going to have to do. But your objective is to figure out, design an experiment that's going to let you know what is this solid and what is this liquid. So let's go ahead and kind of miniaturize this a little more. And that's the best I can do there. Okay, there, like that. Hopefully it shows up better when it goes up on YouTube. So if you can't see it now, you can always rewind the video later. It should show it on the big screen, more zoomed in. All right, so our first experiment then, the first thing is your question. What's the question? Yeah, what is the unknown? And you have two unknowns, don't you? You have the liquid, and then you have the solid. All right, so what is it? What is the unknown? So that's really the question you're trying to answer. So the next thing you have to do is come up with a hypothesis. In this case, you don't really have a lot of data. You could have looked, like what some of the kids did in the other classes, they looked at the solid, and because they actually were able to start the experiment in class, they weren't able to finish it. But they looked at the solid, they made some observations before they did any experiments. And they compared them to their observations of the other solid, because they made I saw some really detailed observations of both solids, like one was more powdery than the other. If you looked at calcium chloride, you saw it was more like a salt. In fact, it is a salt. And you see calcium carbonate was more like chalk dust, because it is chalk dust. So calcium carbonate and calcium chloride, when you looked at the two, they look very different. And somebody else noticed that when they did that part of the experiment, they noticed that the acetic acid smelled like vinegar. So some people noticed that information, so writing it down, that gives them a hypothesis, right? That lets them be able to make an educated guess. Remember from the test, as you go over your test questions, an educated guess, a guess as to what something is your hypothesis. Hypothesis. So, yeah.
What is the difference between a hypothesis and
A hypothesis is a guess based on some observations. All right? An if-then statement is how it's written usually, but it's not always written that way. So somebody said for the test, you didn't write in an if-then statement, so I didn't know it was a hypothesis. Well, first of all, it wasn't a hypothesis. Secondly, the second thing is, if I define a hypothesis, the definition of a hypothesis is not an if-then statement. All right? When you write a hypothesis, it should be an if-then statement. Can I write you an example of a hypothesis? And then we'll go on to theory later. Yes? Hopefully. A hypothesis would be written as if the unknown, see how it's related to the question, is acetic acid, then, you see the if then? Then what? Based on your control groups, you're going to have to compare it to something. What is it? What should acetic acid, if then, right? What should the acetic acid be? If the unknown is acetic acid, what should happen? Say what? Say again? If it is acetic acid, what should happen? Then when added to calcium carbonate, there should be actually, let me rephrase that. Should be, you know what? When added to calcium carbonate, gas should be formed. And what? What else do I know if it's acetic acid? Anybody? Okay, the solid should dissolve, but it shouldn't dissolve. That's not dissolved. It should react. It should change into a gas. Yeah. That's very good. Excellent. That's perfect. That's right. So those were our control groups. Then when added to a pH indicator, phenolphthalein in this case, right? There should be no color change, right? Do you agree? Based on what we just talked about with our control groups? So in each of these, what we're doing is we're taking what our experimental results are. What are our experimental groups? It's what we mix our unknowns with, the stuff that we don't know is going to happen, right? When we don't know what's going to happen, that's our experimental group. Our control groups are the groups that we know what's going to happen. We've already tested it. We know what happens if this is this, and we know what happens if this is that. Does that make sense? Yes. So however you design your control groups and your experimental groups, you have to have control groups that you can compare your experimental groups to, or you can't, or it's not science, right? One of the main things in it, well, it's not true. That's not the only form of science, but it's not a controlled experiment. So controlled experiment is when you're using and you're controlling, you have some groups you're comparing your unknown to see, hey, look, it happened then, it changed color there, it should change color here if it's a base. If it's an acid, if your hypothesis is a base, then you would say there would be a color change, right? And then you do the same thing with your hypothesis for your solid, your unknown solid, right? Is everybody okay with what we're saying here?
Yeah.
Now, there was a really good question. What is the difference between a hypothesis and a theory? Write this down. I said it earlier a couple weeks ago, but anybody remember? That's right. It's a well-tested experiment. Well-tested theory. A theory is a well-tested scientific idea or relationship, right? So, and a hypothesis is a scientific guess. If this is going to happen, then that's going to happen because I did it before, and that's what happens when I did it before, so I expect it to happen again. Say again? A theory? Do you want me to write it down then? A theory, you know what, let me just change pages because this is getting kind of crowded here. So, a theory, all right, is a well-tested let's use another word. Let's use the word pattern, comma, relationship, column, concept, right, in science. So anytime you have a pattern that you have tested over and over again, that you develop a relationship. You say, look, every time you add an acid to a base, you produce carbon. You have a neutralization reaction. That's a theory. Every time I add an acid to a base, this is what happens. No matter what, if I form gases or not, the acid turns neutral. The base turns neutral when I mix the two together. That is a theory, right? It's an idea, and it's well tested. So what do I mean by tested? I mean, you did it in your country, you did it in your country, you did it in your country. Let's assume we're scientists all over the world, obviously. You did it in your country, you did it in your country, right? And everybody all over the world does it. They mix acid and base together, and they get neutralization reactions. It's a theory. It's well tested, no matter how many times you do it. A theory becomes wrong when what? When somebody does mix the two things together and you don't get those results. Does that make sense? So that's that. But you know, when we have a theory in science, it's been well tested. Usually thousands of experiments, thousands of individuals, hundreds of years. The theory of evolution, people say, oh, it's just a theory. The theory of evolution is hundreds of years old, with hundreds and thousands of different experiments and relationships and evidence, all collected, all put together in one body of evidence. That's a theory. Now, could someone discover something that disproves it? Sure. It'd be difficult because there's so much evidence to support it, but it's possible, yeah.
Is there different definitions of theory? Because when we're doing experiments, of course, after we get the evidence, we either have to change our theory or we can keep it the same way. So that's right.
Usually with the word theory, you're talking about conclusion, right? So when you're talking about your experiments, you come up with a conclusion. Usually we reserve the word theory for something that's well tested. So it's not just your conclusion from your experiment, it's a conclusion from thousands of other experiments as well. So we change our conclusions all the time. And our theories change all the time. Who here learned Newton's laws of motion? Right? You guys learned it in middle school. He was wrong. Einstein proved it. Einstein proved that Newton's laws were not accurate enough. Newton's laws of motion are not accurate. Einstein disproved his laws. Why do we teach it to you? Because Newton's laws are easier to use and they work at our scale on the planet Earth. When you get really, really big, when you try to predict the motion of Mercury around our solar system, or you try to predict the movement of electrons at the quantum level, Newton's laws fall apart. On the other hand, Einstein's laws, you can apply them to everything, but you then have to use calculus to try to do it, and then people get confused. And so we say, let's keep it simple, and let's use Newton's laws for our everyday work. But when we start to use, we all have to understand that Newton's laws are not have been proven wrong already. We've already changed those rules, and that's why we use Einstein's laws when we have to get more exact. Yeah.
So, if an experiment is on the test of once, would that be considered a theory?
Say that again.
If an experiment is on the test of once, would that still be considered a theory?
What a great question. It's actually the essence of science, right? You should write that down because that's evidence of you. What? What's the evidence of you? Which 6R is that? Was that a great question that came from her own mind? It's not reduction because she didn't reduce a big list to something small. What did she do? She reflected. She reflected and came up with a great question. That's really the essence of reflection. So, in any way, she reflected. Her question was, if something's not testable, can it be a theory? The answer is no, not in science. In science, whatever your theory is has to be testable, or it's not science. It could be something not outside of science. So usually the way we do it, and it doesn't mean, by the way, no one's making a judgment call here, at least not in this classroom. I know that there are people out there that make judgment calls all the time. But let's not make judgment calls. That just, all it means is it's either testable or it's not testable. So if it's off the circle. If it's testable, we call it science. So it has to be testable. If it's not testable, it's not a hypothesis, it's not a theory. You have to be able to put in a if-then statement, right? To be able to test it. You have to be able to do an experiment that shows, is that relationship correct or is it not correct? Now there are things that are inside this. For instance, motion, right? We can check Newton's laws of motion. Chemistry is in here too. If you think something, the unknown, right? We can use science to discover that. But there's stuff that's outside this circle, right? There's stuff like ghosts. Forget about it. We can't test for ghosts. ESP. And no, the TV shows that you see with the infrared cameras, no. What testable means is that if you can go to a house and you can identify a spirit in that house with some kind of test, I should be able to go into that same house with the same test and find that spirit. Does that make sense? That is science. If you go somewhere and you find a ghost and someone else goes there and doesn't find a ghost and you say, oh, it's because you're not open to it or whatever, that's not science. Okay? I'm not saying it's right or wrong. I'm not making a judgment call. I'm just saying it's not science. Obviously predicting the future with, what's the other thing? Astrology. Good, because I only have one more thing to say. And of course, religion, right? Religion's out here too. Now, I put religion outside the circle of science. Does that mean I think religion's wrong? No, I'm saying it's not science. So let's be clear on that. I don't want to offend anybody. People believe what you want to believe, but it's not science because we don't test our religion by definition, right? It's a matter of faith and belief. Science, I hate it when people say, do you believe in Darwin's laws? Do you believe in Newton's laws? Do you believe in science? I don't believe in science. I use science to understand to have a temporary understanding of what's going on right now. My belief is something completely different. So 2 different circles, all right? All right, so that's it. I hope that helps. And make sure you get that homework done, and I will post this. Attendance is done. Time's up.